O'Shea's data supports this because lactate levels decrease at 3 minutes, which suggests lactate was made in the first 3 minutes of exercise, as the cardiovascular system could not meet the demands of the respiring tissues, as the ATP-PC system would have been in use as it creates lactic acid as a byproduct. O'Shea's data also supports that lactate levels will remain constant, as there is an overall difference of 9.5% change in lactate level between 11 and 18 minutes, which is where, interestingly, the heart rate was most commonly maintains a plateau as well. Blood pressure. Systolic blood pressure is the pressure exerted from the left ventricle to pump blood around the body. During steady-state exercise, systolic blood pressure increases. This is because the heart rate increases, which also increases blood flow. Because of this, pressure within the arteries increases as the force exerted on the vessel walls increases due to the increased blood flow. Diastolic is the pressure within the right atrium in the filling stage of the heart cycle. This usually stays continuous during steady-state exercise. However, diastolic pressure can sometimes even decrease when blood vessels vasodilate to increase the volume, therefore decreasing pressure. A vascular shunt is the distribution of blood around the body. It occurs during exercise. The vascular system sends blood to certain areas in the body with the greatest demand for oxygen, respiring tissues, and away from areas with lower demand for oxygen by either increasing or decreasing the diameter of blood vessels via vasoconstriction or vasodilation to increase the blood flow to certain muscles. According to ZocDoc, blood vessels within the muscles are you are using expand due to vasodilation. These two countering effects cause a rise in your blood pressure, systolic. Also, according to National Sport and Exercise Science, diastolic blood pressure stays the same or decreases slightly. Hypothesis for blood pressure was systolic blood pressure would increase when exercise begins, and diastolic pressure will not increase. And the method was use a blood pressure monitor before and immediately after exercise to ensure after exercise to measure systolic and diastolic blood pressures. Normative data suggests that systolic pressure is proportional to intensity and will increase by about 20% during steady-state exercise. This means a small increase in systolic pressure will occur. Although steady-state isn't the most intense exercise, it's still moderate intensity and is certainly more intense than at rest, meaning we will observe a small increase in systolic pressure. O'Shea's data supports normative data, as his systolic pressure increases by 10.3%. Normative data suggests there will be a minimal increase with diastolic pressure during exercise by about 6.3%, and will then decrease by about 4.8%. O'Shea's data supports this, as his diastolic pressure decreases by 17% after 20 minutes of steady-state exercise. During steady-state exercise, cardiac output increases because heart rate increases. This results in increased volume output of blood every minute. However, once the cardiovascular system is meeting the demands of the respiring tissues, supplying an efficient amount of oxygen in the blood to the muscles, normative data suggests cardiac output can reach between 4 and 8 litres per minute. However, a professional athlete like Mo Farah, with a resting heart rate of 33 beats per minute, shows he has a very efficient cardiovascular system, as his heart can supply his muscles with enough oxygen at rest in 33 beats per minute, which also suggests he has a very low cardiac output as well. According to Nursing Centre, the normal range for cardiac output is about 4 to 8 litres per minute. The hypothesis for cardiac output was that it will increase during steady-state exercise. Cardiac output can be calculated by getting your heart rate and timesing it by stroke volume. Borg scale. During steady state exercise, the Borg scale is used to measure the intensity of the exercise. As the performer will read out a number between 6 and 20, depending on how hard they're working. In steady state exercise, we shouldn't experience numbers above 13, as steady state exercise is moderate intensity. The hypothesis for this was there will be an increase of 1 or greater in the first minutes of exercise from 6 on the Borg scale. It will then be used to plateau, or it will be then seen to plateau on a graph at 3 minutes. The method was to ask the participant to rate how hard they're working on a scale of 6 to 10. Energy systems during steady state exercise. During steady state exercise, the aerobic glycolytic system is used as this exercise is carried out in the presence of oxygen for the majority of the run. The aerobic system, however, starts as it breaks down stored glycogen into glucose. Glucose is then converted into pyruvic acid by glycogen phosphatase, which is an enzyme. During aerobic exercise, oxygen is present, so coenzyme A and pyruvic acid make acetyl-CoA. Oxaloacetic acid is then released from the Krebs cycle and reacts with the acetyl-CoA to make citric acid. Citric acid is then released into the Krebs cycle, which makes a total of 4 products. These consist of more oxaloacetic acid, which is then used to convert more acetyl-CoA into citric acid. CO2 is also released from the Krebs cycle along with hydrogen and 2 moles of phosphate to convert some ADP into ATP for energy. The hydrogen then reacts with 2 enzymes, NAD and FAD. This then makes NADH and FADH, leaving positive and negative hydrogen ions. The H plus ions make water, and the H minus ions make 34 moles of phosphate to make lots of ATP from ADP. This is leaving positive and negative hydrogen ions, and this is why we can last longer during aerobic exercise than anaerobic exercise, because at the end of aerobic exercise, the energy system makes 34 moles of phosphate rather than 2 moles made after the anaerobic energy system. However, in the period where the heart rate is still increasing, as to meet the demands of respiring tissues, ATP may be used in those first few minutes. This is because the heart cannot supply oxygen to respiring tissues fast enough in this period, which could result in a very small increase in lactate at the beginning. Normative data suggests, picture on the right, that lactate levels do increase in the first minutes of exercise, as the ATP system in the muscles is used first. Because of this, lactate is made as the heart and breathing rate have not yet reached their optimum rate to support the demands for oxygen by the respiring tissues. However, after 3 minutes, normative data suggest that cardiovascular system is now meeting the demands of the respiring tissues. So lactate levels stop increasing as the body is now using the aerobic glycolytic system with oxygen where no more lactate is made. O'Shea's data supports this, as his 3rd minute reading scores high for lactate level and decreases by 67% after 8 minutes. However, the 11th minute to 18th minute had a decrease of 9.5%, which suggests a plateau. The high lactate reading at 3 minutes can be explained by O'Shea's high Borg scale reading as they continue to increase, which suggests he was not exercising at moderate intensity. Neuromuscular contractions. Muscle spindles are found within muscle and are types of receptor which detect changes in length and velocity of your muscles when moving. They send information via nerves which carry the information towards the central nervous system. Muscle spindles are activated when they stretch as a result of muscles lengthening. Once activated, they send signals to the spinal cord, which then results in more motor neurons at spinal level that then send an impulse back to the muscle in response to the impulse. The muscle then contracts with more force, preventing the muscle from overstretching or stretching too forcefully, as the speed at which the muscle stretches is reduced. Golgi tendons. Golgi tendon organs are also a type of proprioceptor, however located in the tendons of the muscle. They are stimulated when the tendon of a muscle stretches. Muscles relax during a stretch, so deeper stretch can be achieved in the muscle. An example of this could be during stretching. When an individual stretches their muscles, Golgi tendons will detect this and send the information to the central nervous system, which will then send an impulse back to the muscle, which causes the muscles to relax. This prevents injury when lengthening a muscle. Neuromuscular responses to steady-state exercises. Impulses are sent to the muscles from the brain via motor neurons in the body. This impulse will travel down the axon, body of the neuron, to the motor end plates, which attach to the muscle fibers, but not directly. Once the impulse reaches the motor end plates, there is a synaptic cleft at the end, which is between that and the muscle. Within the synaptic cleft is a substance called acetylcholine, which the impulse can travel across to reach the muscle fibers. The impulse then stimulates the muscle fibers, and one motor neuron can stimulate multiple muscle fibers. However, there is a theory called the all-or-nothing theory. This is when, if the impulse is not above the threshold, none of the fibers connected to that motor neuron will contract. A group of fibers connected to a motor neuron is called a motor unit. However, if it is above the threshold, all the fibers in that motor unit will contract. Blood flow. During steady-state exercise, blood flow increases. This is because blood vessels vasodilate, increase in volume. This is because baroreceptors in the aorta pick up on increased pressure. They then send signals to the medulla oblongata to increase the volume of blood vessels to increase the blood flow. According to Sharecare, blood flow is greater when you exercise because the blood vessels in your muscles dilate. And the hypothesis was blood flow will increase when exercise begins. Thermoregulation. Thermoregulation is the body maintaining optimum internal body temperature. It also responds to external temperatures by adapting and changing the internal body temperature. Steady-state exercise causes the body's temperature to increase due to respiring muscles releasing heat as a waste product. Plasma volume increases, which causes the body to sweat out excess water in the blood. This will help the body to regulate body temperature during exercise, as the sweat that evaporates off the body also releases heat energy, cooling down the skin's surface. After exercise, when the muscles finish contracting, they are no longer releasing heat, therefore the body temperature will lower. Starling's law is the law that suggests that as the volume of blood increases in the heart's ventricles due to increased muscular pump, increasing venous return during exercise. The cells in the heart then stretch, which in turn increases the pressure and then volume of the blood that is forced out of the heart, therefore increasing the stroke. Venous return.